October 21st, 2016. People across America wake up and the internet is gone. Twitter, dead. Spotify, dead. Reddit, Netflix, PayPal, dead. But here's the eerie part. Every one of those websites was actually up. Their servers were running perfectly. What died that morning was something almost nobody thinks about. The system that turns names into addresses. Remember the internet video? Machines find each other by IP address. Numbers, like 172, 217. Nobody wants to memorize that. Humans want Netflix.com. So between you and every website stands a translation system, the domain name system, DNS. It runs about 100 trillion lookups a day. It's invisible when it works, and when it breaks, the entire internet disappears while running just fine. In the next 15 minutes, why the phone book is chopped into a planet-wide hierarchy, the treasure hunt your laptop runs every time you type a name, the caching trick that makes it feel instant, what you're actually buying when you buy a domain, and how attackers poison the phone book itself. Let's start with the problem that created it. In the beginning, the 1970s ARPANET, the phone book was literally one text file, hosts.txt, maintained by one organization at Stanford, listing every computer on the network. New machine? You called Stanford. Every computer downloaded the whole file, regularly. And for a few hundred hosts, it worked fine. Then the network started doubling. By the early 80s, the file was huge, updates took weeks, name collisions multiplied, and the download traffic alone was choking hosts. The single-file model was dying of success. In 1983, Paul Macapetris designed a replacement, and his insight was not make a bigger file. It was, nobody should hold the whole phone book. Split the names themselves into a tree and delegate. Read a domain name backwards, and you can see his tree. www.wikipedia.org, rightmost first. Org, the top-level domain. Inside org, Wikipedia. Inside Wikipedia, www, one particular server. Every dot is a boundary between kingdoms, and each kingdom manages only its own children. Nobody holds the whole book. Each holds one page and pointers downward. Fun detail hiding in plain sight. Technically, every domain ends with one more dot. Wikipedia.org dot. An empty label at the end, naming the root itself. Your browser lets you omit it, but type it explicitly and everything still works. That invisible trailing dot is the root of the tree, present in every web address you've ever typed, silently. At the top sits the root, the only level everyone must agree on. Officially 13 root server names, operated by 12 organizations. In reality, over 1,700 physical copies scattered across every continent, all answering identically. The root knows one thing only: who runs each top-level domain. It's the smallest, most replicated, most protected database on Earth. And why exactly 13 root names? Not mysticism, a packet limit. Early DNS answers had to fit in one unfragmented UDP datagram, 512 bytes. 13 server names plus their addresses was the most that could squeeze into a single packet. A constraint from 1980s networking, frozen forever into the architecture of the Internet's most important list. Engineering history fossilizes in the strangest places. Part 2. The hunt itself. You type wikipedia.org and press enter. Your laptop doesn't know the address, so it asks its recursive resolver, usually your ISP's, or a public one like 1111 or 8888. Recursive is the job description. This server promises to chase the answer down for you, wherever it hides. Actually, one stop happens even before the network. Your computer still carries a descendant of that 1970s file, the host file. It's checked before any DNS query, and it overrides everything. Developers point domains at test servers with it. Ad blockers route tracking domains to nowhere. Malware, when it sneaks in, uses it to hijack your bank's name. The original phone book never died. It lives on your machine with veto power. The resolver starts at the top. Question to a root server. Wikipedia.org? Root. No idea, but here are the servers for .org. Ask them. That's a referral. and it's the engine of the whole system. Never a full answer, always a pointer one level down the tree. Next stop, the .org servers, run by a registry that manages every single .org name. Same question. Answer, not mine to say, but Wikipedia.org's official servers are these. Ask them. One more hop down. Notice nobody's guessing. Each referral comes from the level that OWNS, that slice of the namespace. Final stop, Wikipedia's authoritative name server, the one machine category with the actual answer, straight from Wikipedia's own DNS records. Wikipedia.org? That's 103.102.166.224. The resolver hands it to your laptop, your browser opens a connection, the TCP handshake from our internet video, and the page begins to load. Notice the protocol choice underneath. Those questions ride UDP, the no promises sibling from our internet video. Why gamble on a lossy protocol for something this critical? Because a lookup is one tiny question and one tiny answer. A TCP handshake would triple the round trips before saying a single useful byte. If a packet vanishes, just ask again. Asking twice is still cheaper than shaking hands once. Right tool, brutally chosen. For questions, 4 answers, across potentially 4 continents, in about 30 milliseconds. But here's the thing. If every lookup really did all 4 hops, the root servers would need to absorb the entire internet's curiosity, 100 trillion questions a day. They'd melt. The system survives because of one trick, and it's the same trick as the CPU video, caching. Every answer in DNS travels with an expiry date, the TTL, time to live. Wikipedia is at this address. Trust this for 1 hour. Your resolver remembers it. Your operating system remembers it. Even your browser keeps its own little phone book. Next lookup, answered from memory, in under a millisecond, 0 network packets. The treasure hunt happens once. The memory serves millions. The TTL is a dial with a real trade-off. Set it long, a day, and the world hammers your servers less. But when you move your website, stale caches keep sending visitors to the old address for a day. Set it short, 60 seconds, and you can migrate almost instantly at the cost of constant relookups. This is why DNS propagation takes hours. Nobody is pushing updates. You're just waiting for a billion caches to expire. You might wonder how one address like 8888 can serve the whole planet with 5 millisecond answers. It can't, so it's not one place. Anycast routing announces the same IP address from hundreds of cities, and the internet's routing, remember BGP, naturally delivers your packet to the nearest copy. Same address in Tokyo and Toronto, different machine answering. DNS resolvers, root servers, CDNs, all of them are everywhere at once this way. Resolvers, even cache failure. Ask for a name that doesn't exist, and the authoritative server replies, in X domain, no such domain. And that no gets cached too, with its own TTL. Otherwise, every typo on Earth would hammer the root servers forever. Think about that. A measurable fraction of the internet's most critical infrastructure is dedicated to remembering, efficiently, that things do not exist. Caching also explains the 2016 blackout from our cold open. The attack, a botnet of hacked webcams, didn't touch Twitter or Netflix. It flooded Dyn, the company running their authoritative name servers. As cached answers expired across the planet, resolvers went back for fresh ones, and no one answered. The websites stood in the phone book with their pages torn out. That's DNS, not the destination, the only way to find it. So what's actually written in the phone book? Records of several types. An A record, named to IPv4 address. Quad A, the IPv6 version. CNAME, this name is an alias for that one. MX, email for this domain goes there. And TXT, freeform text, which the modern web uses for everything from spam protection to proving you own a domain. DNS also quietly became the internet's traffic director. Big services return different answers to different askers. Query from Istanbul, get the Frankfurt data center. Query from Ohio, get Virginia. Ask twice, and the answers rotate through a pool of servers. Load balancing by phone book. That's the machinery of every content delivery network. The name doesn't just locate the service. It chooses which copy of the service you deserve. And when you buy a domain for $12, here's the real transaction. A registrar, GoDaddy, Namecheap, Cloudflare, writes an entry into the registry that runs the top-level domain, saying two things. This name belongs to you. And here are the name servers that speak for it. That's it. You're not buying a website or hosting. You're buying a pointer in the hierarchy, renewed yearly, plus the right to say who answers for your name. The top-level domains themselves have become an economy with wonderful absurdities. Tuvalu, a Pacific nation of 11,000 people, was assigned TV, and licensing it to streaming brands has at times funded nearly a tenth of the government's budget. .io, beloved by tech startups, belongs to the British Indian Ocean Territory. Countries discovered they own beachfront property in namespace. And once the pointer is yours, everything below it is free and instant. Blog.yourdomain, API.yourdomain, anything.yourdomain. You're the authority for your subtree. No registrar involved, no fees, effective the moment your name server answers for it. The delegation that scales the whole system is the same power handed down to you. Your kingdom, your pages, your rules. Now the dark part. DNS was designed in 1983 when the internet was a village of trusting academics, so answers came with no proof of authenticity. If an attacker can answer faster than the real server and guess the lookup's random ID number, your resolver believes them. Cache poisoning. One forged answer, cached, and now everyone using that resolver gets sent to the attacker's server, with the correct name glowing in the address bar. There's an even blunter attack, just like closer to the user. Rogue Wi-Fi hotspots hand your device a malicious resolver along with the free internet. And from then on, every name you type is answered by the attacker. No exploit, no race to win. You literally asked them. It's why public networks pair so badly with sensitive logins, and why the encrypted handshake from our TLS video, which checks identity, not just the name, is the real last line of defense. In 2008, researcher Dan Kaminsky found a way to win that race reliably and poison any resolver on Earth in seconds. It was arguably the closest the internet has come to a total trust collapse. The fix was historic. Every major vendor patched in secret, in a coordinated release, and the long-term answer, DNSSEC, adds digital signatures to DNS records. Remember signatures from the encryption video? Each level of the tree signs the level below, a chain of trust from the root down to your domain. Because DNS is the front door, it's also where control gets applied. The cheapest way to block a website isn't to attack it. It's to order the country's resolvers to forget its name. In 2014, when Turkey blocked Twitter this way, the workaround spread as graffiti, walls stenciled with 8888, Google's resolver address. Switch your resolver. Escape the localized amnesia. A phone book you can choose is a freedom most infrastructure doesn't offer. One more modern shift, privacy. Classic DNS travels as plain text. Every network between you and your resolver can read, log, or rewrite the sites you visit. That's how some ISPs sell browsing profiles and how captive portals hijack you. The fix is DNS over HTTPS. Your lookups ride inside the same encrypted TLS tunnel as web traffic. The phone book finally got an envelope. Let's fold the map. Names live in a tree. Root, top-level domains, your domain. Resolvers hunt down the tree by referral and cache what they learn, guarded by TTLs. Buying a domain buys a pointer. DNSSEC signs the pages. DNS over HTTPS seals the envelope. And the whole thing handles 100 trillion questions a day without a headquarters, without a master switch. The same anarchic elegance as the internet it serves. And here's the quiet lesson in Maka Petrus's design. The way to scale a system beyond imagination is to give away control of it. One file under one organization died at a few thousand names. A delegated tree, where every kingdom runs its own page, scaled a billion-fold on 1980s ideas, and it's still not the bottleneck. Decentralize the data, cache aggressively, trust, but verify. Half of modern system design is in that sentence. And you don't have to take any of this on faith. The whole hunt is observable from your own terminal. One command, dig or lookup on Windows, shows you the answer, the TTL counting down, which server replied, even the full referral chain from the root if you ask for it. Run it twice and watch the TTL drop. That's the cache, aging in real time, right in front of you. So the next time a page can't be found, you'll know the real question. Is the site down, or did the treasure hunt fail? Flush your DNS cache. Try another resolver. Check whether the name even resolves. You now speak the language, and you can diagnose in seconds what most people just refresh at. The Internet's phone book, born from one text file, scaled to a planet, still running on delegation and memory. More invisible machinery next time. See you there.